while we're setting up, I can actually make a couple of announcements. So after lunch, we'll come back at 2 p.m. We'll have an award ceremony. We'll have a few short invited talks, and then a discussion. And then after the discussion at 3 p.m., we'll have the poster session. So actually, if you're presenting a poster, you should probably put it up during lunch. And and yes, and also if you're one of the speakers that presented in this session, if you could send me slides or a link to slides, email me slides or send me a link or whatever, that would be great, and I'll put it up online. And please give me like a few days to a week because I'm traveling right after this, so everything will be up online, maybe not immediately. Okay, so the first spotlight is from Andrew Howard, who unfortunately couldn't be here. So the results of this submission are mainly driven by a set of 3 models built through multiple stages of adaptation. We started by building a base model using a modified Zeiler-Fergus architecture, extended to 7 convolutional layers and taking 6 weeks to train on a single GTX Titan GPU. This base model is built by training on perturbed random image crops selected from the full image. The base model is then adapted into a high-resolution model with training crops selected from higher-resolution images, and a low-resolution model with training crops built from lower-resolution images. Next, the base model itself is modified by replacing the fully connected layers with new ones that are 3 times as wide. A network this size requires 2-step training because of the memory constraints of a single GPU. We then build the final models by adapting the fully connected layers of all 3 models to a random subset of the validation data. Each initial adaptation takes about 2 weeks, and the validation set adaptation takes less than a day. At test time, predictions are made at 6 different resolutions, with each network being responsible for 2. Each resolution is roughly 30% larger than the previous. For each resolution, image crops from a dense grid are run through the network to generate a prediction. Predictions from each resolution are averaged to form a combined prediction for that resolution. These 6 predictions are then evenly combined to form a final prediction.
Hi there, we are a bunch of 4 guys from Singapore, and 2 of us also belong to a UPMC lab university in Paris. I belong to the Institute for Infocom Research in Singapore. And basically, a couple of months ago, we decided to form our team and managed to find a bunch of GPUs lying around and decided to participate in this. And hopefully, our target was to beat last year's score. So what we did was, we got some pretty old GPUs. And we did CNNs, not so deep ones, so 7-layer standard ILSVRC2014. And we tried to see how is it possible to train very small CNNs and also to combine them. So we did some optimizations to pull between crops and also fuse between models. And subsequently we had some tricks to rectify the scores at the very end. So we eventually managed to combine 11 models pretty well through some optimization. So more details you can speak to me at the poster. Thanks.
Hi everyone, my name is Michal Hradiš. I come from Brno University of Technology, which is in Czech Republic, and we started working on deep learning this year, a few months ago actually, I worked with Martin Kolář, Pavel Svoboda, Pavel Zemčík, and for some reasons we have very many Pavels. As we really are very new, we started with a sort of baseline, so we have baseline deep convolutional network, Marvin Cafe, we transport images in a random way, we average responses of those transport images, we train some variations of the standard baseline architectures, and again we average those in a weighted way. Weights were fed to the validation set. We were surprised how well we did actually in the localization. We really had just fixed localization window, which was in the middle, and it was 55% of the image, which seems to be like the correct way to do fixed localization. And that's it. We are quite new, so if there's some group who wants to collaborate with us, we would be very happy to talk to anyone. Thanks.
Hi everyone. Our team name is Kirby and Keist. When we decided to attend the ImageNet challenge, the period of less than 1 month was given to us. Therefore, we proposed the efficient method to maximize the performance within the time limit. So, in the classification task, our system has 3 key features. First is global expert. It is based on deep convolution neural networks. And second is a local expert. It is to complement the weakness of the global expert. Finally, we use KNN-based and IDF-based reweighting schemes, and then we selected the best ensemble of the 2 experts. Our localization method is very simple and efficient. Firstly, we fine-tuned the classification network to be a bounding box regressor. The output in the regressor is 1 bounding box in each sub-region input. So finally, we can get a score map from a voting system, and then we threshold it. Our system achieved 46.9% error in localization task. Please visit our poster for more details. Thank you.
My name is Hongyang Bai from the Omni Lab Beijing. This is the second time we participated in the competition. I feel we still in the compared last year we have a big improvement, but we have still a gap between the team. And in DT, in the detection task, we also use the ROS framework. The difference is we do not use the SVM method. We just use the neural network output. And in here we find that a team, the negative mining is very important. And from the result we use the negative training get at least a 5% improvement. And in the location, we also use detection framework. We first use the select search and others similar with the general framework. And we also developed 2 app and in the Google Play, and we also have the web demo because the demo is in the server in China. So if you test, maybe the speed is not so fast. Next step we will use the adaptive framework to get better speed. Okay, thank you.
Hello everyone, my name is Koen and I work at Qualcomm Technologies Netherlands. I'm here to present the work of the University of Amsterdam UVision team, which consists of Daniel Fontijn, Kees Noek, Harro Stokman, Arnold Smelbers and myself. My colleague will be demoing the Impala app this afternoon during the poster session, where we do deep learning on a mobile phone. And I will be the poster presenting our work on the detection task. So if you want to know about last year's system, which you won back then, and how that compares to this year's task, we've made a comparison. And we've also ventured into deep learning for detection. But while it says deep learning here, after the presentation of today, we all know that our approach is actually quite shallow. So thank you very much, and I'll see you at our demo on poster.
Alright, that's it. We'll see you at 2 p.m.
Pauze om een nieuwe slide te geven. Een nieuwe slide te geven.